here. And the first talk this morning is opened by one of the chairs of the lab, Ngô B, Châu, and he's speaking on generalized Hitchin, fibration, and invariant theory. So,
most couple of invitations. Thank you all for coming. And so my my talk will be pretty much a continuation of talk I gave at the opening conference of this laboratory. Maybe 2 years ago, we also think in between the pandemic. I remember I gave that talk from Vietnam on Zoom. So since then, you know, we made a really good progress. So I'm very happy to report on that. And the progress will be made by from my collaborator and student in Chicago. I mean, you're very far from completion of anything, but there are some elements that makes me feel more optimistic. It should be there's something. So, but before discussing why and how we should consider this generalized Hitchin fibration, let me recall the Hitchin fibration reform, you know, from my point of view, how I studied it. It's slightly different from how Hitchin is the same thing, but you know, slightly different from how Langlands conceive it. We start with a situation, very classical situation, invariant theory, that is G reductive groups. Defined over field K, and we can assume that characteristic 0 in these talks. For an application of homomorphic form, really want to get characteristic P. And G act on Lie algebras by the adjoint option, right? And we know by the Chevrolet restriction theory that you know, you can embed the carton. So if T is the maximum torus and gothic T is Lie algebras, then T is embedded into the algebras like diagonal matrices, embedded into the whole matrices, and the separation is about the restriction function, invariant function on the Lie algebra to the carton subalgebra, and it says that when you restrict, you know, invariant function, then you get exactly the subalgebra on the top-down algebra, which is stable by the absolute of Y group. So Y group is normalizer of T divided by T itself. So this is really one of the most basic and important theorem in classical invariant theory. All right, and also we know that now the Y group act on this as reflection group. So the invariant is polynomial algebras. So that's why it is A1, A2, AN, where N is at the rank of the group, the reductive block of G, and A1, A2, AN. Here there's a couple of some choices to be made to these coordinates. So they are homogeneous invariant functions, and whose degrees is absolutely canonical. They are the related exponent of the root systems. So this is the part of the classical invariant that we need to and then now if X is a smooth, now just a very slight slight change of view on this. So we think of this thing is a scalp quotient, usually noted by G mod G, invariant theoretic quotient, that the quotient can be built out invariant function. This is a finite algebraic right, is a finite type, but there is a quotient of G mod G. Somehow the most economic where we lose as least information as possible, which is the stack. So it's kind of a group with quotient, and you have this map. Right? And so this is when you have any action, you have this stack quotient, and this is not a scheme, but it can be the best approximation in the word of a fiber, which is this invariant quotient, and have map from start to this. And so the rational theorem is give us some kind of description, not description of this invariant theoretic quotient. And you remember that you also have an action of GM. So GM by homotest, by scalar multiplication on the vector space G, and it acted this by it acted a affine space, but the action is given by this integer. So if I cannot make very much have t. Now it's in K star, it's not the same t. I mean, I cannot make the difference with the chart, but in later it's easier to do it. And so t, if you act on A1, A2, AN, is t to the u A1, EN, GN. And so we have this so GM action commutes of all these adjoint actions. And what you really want to think of is this map from this quotient of G by two groups. And here you're not going to check the invariant quotient because there's nothing less left. We are going to rather to check this. So this is a bit formal, but which keep the same vector space, but we remember the GM action. So this is the setup from the somehow invariant theoretic. And now X is going to be a smooth. Okay, and you really want to look at the map from X to this. You want to study the space or the start map from X to this quotient, and this is a map from phi from X to the quotient, so that when you compose with the obvious map to the classified space of the multiplicative groups, that gives us the canonical bundles. This is the Lie bundle is the canonical bundle. And it basically definition how to unravel what is this map. It might be the same as a map to B of G. That is the E and phi. And E is the G bundles over X, and the lifting to this is P is going to be a global section of X into the adjoint bundle of P, is that by the canonical bundle. Okay, so we can come back to the original notion of Higgs bundle that was introduced by Langlands and Hitchin. And so we have this M is going to be the moduli stack on this object, and it's very standard to prove that it is smooth and no, it's algebraic stuff, locally finite type, so on. And projected now to be pretty smooth. And so when you have this object, you can compose into this space, right, which is simpler. It touches a phi space divided by some weight that action of GM. And so this is the Hitchin map. And now is it just A is from H to AN divided by GM, which leave over the map over the canonical bundle also. And it's very easy to unravel this, and this is the same as the sum of the global section of UK and the power of the canonical bundle. All right, so well, of course, here they have two objects that is deserve to be studied. They have the moduli stack, and but there's also the moduli space of Higgs or semi-stable Higgs bundles, and which is another object that have also Hitchin's fibration. But I'm more, at least for the moment, I'm more interested into the moduli stack. That's very extremely interesting for other reasons, and probably more difficult, much more difficult than the stack itself. And the interruption of the moduli experiment is actually extremely interesting, as pointed out by some spectacular work of Gordon Dickinson and Ziegler. All right, so so this is as Hitchin pointed out from the very beginning that it has very beautiful structures of complete integrable systems, and H, the genetic fibers of H, are essentially abelian scheme. I'm saying essentially because first of all, it's not a group. To make a group, need a base point, and that is in this case given by Hitchin section. It's dependent choice of the square root of K. Also, we need so it now it become a group, but it may not be connected. So there's some kind of the group of connected components, and there's on the moduli stack we also have some isotropic groups, and so those is very important. But for more just theory and SML schemes. So what was very crucial in my own work is as a complete integrable system, you have the Hamiltonian action of the vector field. So, but it is actually in this case there's this you have group action, not just the vector field action, and you can define it, and you can introduce the critical Tika action. So some another piece of data, the structure of some type P, which is the smooth group scheme of smooth Tika stack, and P is equal to up and M fiber-wise. And the tangent level, that is the Hamiltonian action, but we actually have a canonical group action. And how to define this P, and then you actually come back to invariant theory, right? And I try to economize my make use. So maybe I'm going to erase something from the. I'm going to erase this. Don't need to remember about this degree anymore. So we have the So you have G, and you have this invariant quotient G mod G, which is the same as T mod W. So this is, in this case, this is flat maps, right? And which is but which is not smooth, right? It's not smooth as zero, for example. And every fiber is not a homogeneous space, but rather a union of finitely many orbits at one orbit. For example, the fiber over zero is the union of nilpotent orbits. But there is a very nice open subset here, it's called G-reg, which is the union of regular orbits. So regular orbit are orbit to the maximum dimension, right? And what we know about this is, let's call this is chi, the characteristic polynomial. Essentially, this is chi-reg. And then what we know is that chi-reg is smooth, and its fibers are homogeneous spaces. So in other words, in every fibers of the characteristic polynomial map, there's one unique close object, and that is general, right? When check invariant quotient for a fiber like this, there is a bijection between the point of the quotient and close of it, right? But here it happens that there's only one unique open orbit, right? In this case, the open orbit and close orbit are in bijection. And when you restrict to this open regular orbit, you have this. It become a smooth morphism, and fibers are homogeneous. And this is the first point. And over G, if you have I is the centralizer, so this is a group scheme over every point in the Lie algebra. Just look at the centralizer. And that gives you a group scheme which is rather ugly. It is not smooth, not even flat, because the dimension jumps when you go to the zero, you have whole group G. But over I, by definition, it is flat, and therefore it's smooth group scheme. And one of the main main observation here is that I read descent to T mod W. And that means, if you take two regular matrices to the same characteristic polynomial, then they are conjugate, right? And the conjugation gives you the transportation gives you an isomorphism which is one centralizer to the other. And then to put that isomorphism, that doesn't depend on the transporters. It's mainly because the centralizer is commutative on this. So there exists a unique smooth group scheme J over T mod W equipped with a G equivalent isomorphism from P of chi-reg star of J to I-reg. So that what I mean is descent, and it's unique canonical. And moreover, these isomorphisms extend to homomorphisms from chi to I. This is the main piece of structures, and so every time you have the map from X to the invariant quotient, you can put back, you can A in A, then you can define JA to be the pullback of J to A. I mean, J is, the GM function doesn't respect all these structures, so it can stand with this. And literally define PA to be on the torsors on this PA. All right, and because of this homomorphisms, the PA are canonically unconditional.
You mean torsors on JA?
Torsor GA. So this look very abstract, but it is, you know, on the K of G equal to GLN. This is very easy to see. You know, every time you have A, you have the spectral curve, right? And then and JA is just the pika, the spectral curve. Pika, whereas MA is classified torsion free round one shift on the spectral curve. And of course, you can do by tensor product. The pika out on the compactified pika, right? In this case. But this action actually can be generalized to generally without mentioning the spectral curve. So somehow this control this J equal regular centralizer can give you the way to do many things without ever mentioning the spectral curve. Of course, it's much nicer if you do have spectral curve, but you can do it without in to a certain extent. All right. So this is the main piece of the structures, and what I want to say more is all right. And for example, you can say also that we have this M. Here we have the M rec. And by definition, the M rec is just the map that land into the G rec, right? And M rec is open subset of M. And by definition, PA is up on MA rec simply transitively. So MA rec is the torsor and the PA. And the MA is some kind of compactification with MA rec. So this fact that PA up simply transitively on MA rec can be, you know, reformulated in this language in a nice way by saying this. Saying that when you look at the instead of G, then look at the GI rank. Mod G made to this T mod W, this G mod G. And say that chi-red is smooth, there is fibers, a homogeneous space. This is equivalent to this is the gerb. This is the gerb, and as gerb, it is bounded by some band, and then the band is a group scheme which is well defined up to inner automorphisms. And in that case, this group is commutative, so it's actually the group. And this gerb is bounded by J. That is a regular centralizer. So our definition of J here by hand is nothing but it's just rephrasing this story of gerb and the bound. It's a band bounding this gerb. So, you know, in general situation, that is suggesting that there, maybe, you know, its commutative case is be nice, and if not, you're not going to have a group scheme, but you can have a band. To go up to inner automorphisms. And this is actually this single fact imply in general this MA up simply transitive and MA right? And another fact which is very important to when you want to kind of study the PA in more, you know, to more details is that we have another you know, have an alternative description. Here it appears as just a gerb, as a group bar in a gerb. temperature, bound and cumulative, and you have those smooth group schemes. But to do computation, you want to have some more hand-on. And that is given by the Langlands theory, and it really gives the other description of this restriction theorem. Is you have this map from T to T mod W, and which is what Langlands called in the universal covering, but it's just a map T to this quotient, and this is a flat covering of degree equal to the cardinality of the variable. Right? Generically, it's going to be a torsor under the variable, but it gets ramified, but it still remains flat. And what but I guess we say this, so if you are going to take T, take the T time T, and you see it as the constant group scheme over T and fiber, it must not torus, right? And we do the Weyer restriction from T to T mod W, right? And the Weyer restriction works much better if the flat, otherwise it's pretty bad. Right? And so we have these things over T mod W. Right? Now it's going to be a smooth group scheme because Weyer restriction actually preserves smoothness. And to have smooth group scheme over this base, and the dimension is the dimension of T times the order of the variable, and that the Weyer restriction tells us. But if you take W invariant W, then you get the right dimension. So this is going to be kind of Galway central torus in very loose sense. That doesn't make sense because Galway 7 is not etal, but at least you do this. It's no problem as long as the flat comes. Right? And then let's put this J1. So this kind of approximation of J. And what say when it goes gets great that you have a homomorphism of J to J1. Well, it's more like kind of brief. I mean, in the only way people didn't talk about in this language, but this is how I rephrase the work. So we have canonical map from J to J1, which is an isomorphism on genetic fibers, right? And but the almost an isomorphism in the sense that it induces an isomorphism over the Lie algebras. And so it has the same connected components, but the differences in the very subtle in the connected components. So you can rephrase it very nicely by saying, so this group may have some disconnected fibers, right? But it has the smooth group scheme. It defines canonically a J naught. So a subgroup scheme which is open as as subscheme, open subscheme. As group scheme have connected fiber. This is canonical and if I were every smooth group scheme. And J is actually in between J naught and J1. Right. And so the only way to have a hand on this J precisely is to read the on this pi naught, the difference in the pi naught and fibers. This, and you can do this from some combinatorial and combinatorial root system, where without note that probably make mistake, but the main thing is the description itself probably is not so important, but what is extremely nice in these things is these pictures behave very well with respect to Langlands dualities. In the sense that if you switch from G to G hat and everything switch. So somehow J naught become the dual between J1 and J1 become J naught. And also this group going to be dual to that group. So that gives you actually I think the nicest proof for the important fact that Hitchin fibers for dual Langlands dual group are actually duals in very strong sense. not just dual varieties, but it dual as one motif, have the Bellingson motif. And so this is really, that is what all the invariant theoretic fact it is. That you can, all these connected component group behave very well with respect to Langlands dualities. All right. So then, from this point, when you have put in all these pictures, you can, pretty well understand what PA is, because you have this nice description. This you can, well, you can compute what is the connected component group of PA, and then component group PA. We can understand this is what is the this cumulative group scheme, and what is abelian varieties, and what is the dimension of five group. You can calculate whatever you want to calculate, and so an MA rect is you can know it as long as it has a section, right? And the section is in for classical group is described beautifully in Hitchin papers, but in the invariant theory it really the constant section. You can have constant section here, which is not GM equivalent, but we need to do something for that and come back to that later. And we have you have to play a combine kind of global story for Hitchin fibration, but there's a kind of local counterpart of fast finger fibers. I didn't have time to go into this, but the fast finger fibers give you some information about dimensions. For example, from if combine both story, you know that you can prove that in this case MA red is then into MA, right? And that's very simple. That is very important fact. I mean, the only proof we know how to combine both. You have to get some local information and global information, put them together and get this fact. Because the 5 microfibers, they want to study. For example, you can compute some dimension, but it's very hard to prove some kind of density in a 5 microfiber. But for Hitchin fibers, we have some kind of very good commutative algebra property. They are locally complete the sections because it's smooth math and map to smooth math. And so if you know something about that dimension, you can do something about density. So that is all right. And the point where you start from, I was not studying complex geometry. I was studying automorphic forms and phase formula and so on. So what I'm really interested in is understand the composition of the A star of QN analytic sheaf, right? How to decompose it, understand the irreducible constituent of this. And but of course, I mean, there's so many other fascinating questions about Hitchin fibration that I mentioned. But the setup I just described is very suitable to at least to understand this question about the composition of field. All right, so now I'm kind of ready now to move on to what I call the generalized fibration. So I really want to study instead of action of G on the algebras, I just want to also give them very generous action. So with G reductive groups. Over K, acting on maybe now M. M is no longer the moduli space, but M, this capital M is some affine scheme. A finite tab over K, right? So this is a very usual situation in invariant theory. And in this case, you have M mod G is a spec of the Km of G is going to be a scheme of finite type with this big theorem of Hilbert and Lumsford and all the people spoke about. So we have this And we are going to want to study the whole story, the map from some curve which you did, maybe some twisting, right? Maybe you need to introduce some twisting. You have some, you want to some kind of another action, maybe a torus or something with at least then diagonalizable group. After on M, which is commuting with G. I show you some example where on this come to it. And you want to study a map from X to M mod G times the M. So this is kind of my generalized bundles. You're going to map to this, which is over a given some given ZM bundles. And now the Hitchin maps is going to be compose this thing with M mod G, mod G, and divide by ZM. It's going to be the same. So this is kind of it's very naive way to generalize this, but I think it is really the good object to study. Just a few examples why, and actually, right now we want to study this curve, but actually we really want to study actually some smooth projective varieties. It will be very nice. So X is kind of a curve or even higher dimensional variety. So examples, why you should study this kind of very general situations. We actually have a lot of very nice examples. So one of the most classical examples is the symmetric space, where you have some theta, some involution of Lie algebras. So we have this decomposition of G equal to K plus P, where K is +1 space and P -1 space, and we have the K is complex group and K acting on this P. So this is constant values. This quotient is defined by constant value theorem, which is very classical, right? And it also this kind of situation that we study automorphic form too. And you can study there is some situation which is actually extremely important from trace formula from automorphic form point of view. And it happened actually, what I call the multiple Hitchin fibration that Oscar explained to me after he had been studied in physics mathematics a long way ago, without knowing it. So we look at the when you have reductive group, there's all this theory about monoid, algebraic monoid. Algebraic monoid is a final more algebraic variety with multiplication. And the inverted monoid point is reductive groups. And this is very well studied. And one of the main examples when you start with the mother monoid, the Weinberg monoid, when you start with the adjoint group, and you can look at the continuity processes, wonderful compostification, right? And that thing can be have a Picard group. Well, it should Z some powers, and so that we have actually a canonical toxin over that complete varieties, and the total space of these toxins is not affine, but is quasi-affine, and you take the affine closures, you exactly the Weinberg monoid properties. So it's really very canonical, right? And it somehow is kind of just real functions on the universal toxin of the quotient compactification. But it from the anyway, I mean, you have other monoid also, but we really want to actually look at G after M by conjugation. And so in this case, this is called the by the way, this case, in this case, the official name is the Hitchin fibration for real group, right? I've already got confused, but I don't see the real groups.
Involution, right? Group with an involution, let's say symmetric pair.
Yeah, symmetric pairs. groups. And in this case, it's the multiplicative Hitchin fibrations. And in this, in this case, that aim to be the real, the right geometric interpretation of the center trace formula. Right? In this, the algebra is kind of a very simplified version of it, and this is kind of the right one. And this is now studied quite roughly by at least 3 of my students. Studied with you. And continued by Jing, and now it's almost, it's most completed by Griffin Wang. At least the decomposition theorem for this case is, but on this what I tell you is kind of now implemented. I mean, with a lot of difficulties, it's really very hard work, and this is really understood. I think it's really very impressive body of work. 200 pages of proof of the thesis of one thesis. And this kind of Hitchin fibration, this kind is studied a lot by people in Hitchin school for with non-abelian host theory. And, but now it's been studied by in automorphic forms, by Leslie, Spencer Leslie, and so also studied by Heimester, and Benedict. And also, we can also have some kind of multiplicative symmetric space. So we essentially after the K, acting on G mod K, and that is being studied by Oscar and Gallego. But they also somehow this is on the student it is actually much more difficult than the original situation of Adrian Arshel, but it's pretty similar in many space. But there's also kind of depart quite radically from this is the case when we look at M is commuting varieties. The commuting scheme. So M is just space of X1 as D in GD, so that Xij is 0. So this kind of scheme has been a kind of object that we studied quite very long history in invariant theory, but it's still very mysterious. Like we know very little about this. And I mean, last week when I met talked about this in Paris, and after that, Vasco told me that a year ago he met Lixmier in some dinner, and this must nothing. Do we know it is reduced now? I probably don't. Lixmier, 99 years old man, is still very curious about knowing the complete scheme is reduced. Now we don't know it. So anyway, we had the action of G over M, and we actually have also action of G and D on this, because you can form in a combination of these vectors. So this essence can see it as a map from a vector space, D-dimensional vector space to G, which is commutative. Image two vectors. And the bracket is 0. And in this situation, you can this give rise to Hitchin fibrations. For higher dimension varieties. So this is become G and D, right? In this case. So if X is the map, so the map of X to this quotient, if this thing is the cotangent bundle, right? And this is exactly that the vector bundle of dimension n with a commuting absolute tangent bundle, right? Right? That is of the Higgs bundles in higher dimension varieties. So in this situation, this gives rise to the moduli that of Higgs bundle higher dimension varieties. And Hitchin fibration can be defined exactly in this uniform way. But of these kind of, there's many problems. The invariant theory is really hard, right? Because of the very simple fact, all these situations, the M itself is very nice, smooth or normal at least. In this case, you don't know anything about M. M is reducible and may not be. It's very likely it's not going to be reduced. But before you can do that, it's not. But so it's very difficult to do this. But that's one piece of at least when M is normal and reduced, then there's very nice bit of work of lunar retraction. That gives you a description, a nice description of the M1 mod G. Right? I didn't characteristic 0. Right? So let me recall this very roughly because I'm running out of time. So normally reduce it there this one condition that makes this thing work is at least assume there exists at least one regular influence of it. Both close and regular. And this is what the Johnson has assumption. So when it is close, then the stabilizer is going to be a reductive subgroup of G by Matsushima theorem, right? And by Luna slide theorem, it happens that there exists actually a dense open subset of M, where all stabilizers belong to the conjugation, the fixed conjugation class. So this is it implies that there exists a principal open subset of M open, and so non-empty because you assume that there exists one here, such that for every X in M, the centralizer of G of X belong to a fixed conjugation class of reductive subgroup of G. So it's maybe not connected, but the neutral problem is. So let's call this one is H. And so in many of these cases, in the adjoint case, and H is usually a torus. It's the maximal torus here, maybe smaller torus in this situation. Even in this case is really very wide because M is not normal reduced, but there is this principle. There is this principle, the orbit when on this a regular submissible. And we have the and then now we can look at the fixed point at this H. So this is and so just pick one relatively conjugacy at the fixed point, and then under this assumption, they prove, and one more that they look at the action of the normalizer of H mod H upon F, right? And so let's call this thing it's called some kind of variable. This is not, it's not discrete because this H may be not its own commutators, but just call it W. And if W small mod W is irreducible, so W is the pattern algebra in this case, which is can happen most of the time. Then F inside M induces an isomorphism between F mod W and M mod G. So this is the Hitchin theorem. And it actually provides a very effective way to compute this invariant. And one of the things that help to study this theory at the moment, they actually it's very likely that this linear Hitchin system applied to this case. Although the M is not reduced, not normal, nothing, but you can still prove it. Either theorem for GLN, for symplectic group, or total group, so it's very likely to work with generals. So we can so that's why these pictures for computing skills should, there's challenge to study. So this is for the most basic piece of structures. It is M mod G, right? You replace them because the generalization of restriction theorems. So the next steps, we really want to understand what is the regular centralizer. Well, that is how we really have to get a hand on the Hitchin fibers, these group functions. When you realize that actually not, you get kind of stuck. Because this map is not a germ, right? This map to G mod G over mod, it's not a germ. There's no, in every fibers of this, in this case, it's kind of very nice coincidence that there's only one close orbit and there's one regular orbit, and it's very lucky, right? In all of this case, 1, 2, 3 case, there actually has the finitely many regular orbit over one close orbit. In this case, is really wide. There's actually uncountably many regular orbit. So what we do? So this is what work in ongoing work with Morrissey. We actually introduced what we call the regular quotient. In this notation, something in between M mod G and M mod G, you use notations. And the idea actually is very nice, very simple, right? This quotient, which is it is, it's very nice from algebraic point of view, take invariant function. But from geometric point of view, it's kind of bizarre because it just kept the closed orbit. And the closed orbit do not form a separate. It's locally, it's not locally closed, it's a constructible set. Right? So it must, it's a closed orbit, it's much better off looking at the regular orbit, which form an open subset, right? So why don't you take a space which lies with just the point R regular orbit? And it makes sense actually. It needs some very light, just need some very light some auxiliary data to define it. So you can define this space. Well, it's multiplied an algebraic space, right? Whose points are regular orbit, right? So what is somehow in this case so what you want is let me remove this for for each at a time, just remove this. So the thing in this you have is then one, we have a space whose points are regular oblique, then the m rep mod g over n mod over this regular portion is a jerk. Because now over every point is one oblique. And then you have the then you have a band, you have regular centralizer, leave in very general way on this space. And then you can start running the whole game again, right? So but there is a very one sudden point about this definition. The only one is in the case, the typical case is G often itself, the conjugation. If G is not simply connected, it has some kind of unpleasant phenomenon. There's some regular semi-simple element, so it's regular, but whose centralizer is not commutative. It has some kind of extension and some like this element in one. I think this element, right? No, sorry, this element 1 minus 1 in PGN2.
What's a minus I minus plus I?
No, don't let me confuse it. I don't know. Anyway, there's some element in PGN2 whose centralizer is not commutative, and that means that is really real because the centralizer, when you restrict to this, the Lie algebra has the right dimension, but the group is not flat because they have to stick out some known, and they have to remove that stick out. So we need to add into this something which is not the restriction of the centralizer to this, but the smooth part of it, which I had to remove something that is not not flat. And that's it. When you have this additional data to avoid this unpleasant phenomenon, and then you can define this very much in the same way that we descend this regular centralizer here. It just really the same construction we have kind of using firstly flat descending double détente in French. I don't know how it's say in English. Twice, and you can do this quotient. And this also is explained nicely in this case. In this case, the thing is by descent, this one is always smooth, right? As long as m rep is smooth, this one is not smooth. It's just to perform descent. But in this case, in this action, you can G mod G, it's not smooth, right? So what happened is the quotient we construct is in this when the difference between the I and the centralizer, then this is not an algebraic space, but this is the Riemann Foster. And this space is now the kind of the core space underlying the algebraic stack. So this lack of regularity, this quotient is also somehow understood in the difference between the regular quotient, which is smooth and so anyway, we have this, and you can kind of very topological have J, right? And it can pretty much, at least for definition, you have the very similar diagram. So, for example, we have this. I'm almost done, so it's not running out of time. So we have this space of X into the M of mod G, and now we have this thing. Oh, by the way, in this, I have to say that in on this case, most of this case, so let me give one example. The kind of very should have with absolute VM acting on A2 by T of X, Y is Tx T minus y. And in this case, the invariant quotient, which is A1, because the invariant function is X times Y, right? But in the pictures, For x, y equal to 0, we have 3 orbits, right? One closed and 2 regular. So we have to remove the closed one, but these 2 regular orbits represent 2 different points in the regular quotient. So as a result, the regular quotient is in this kind of A1 with 2.0, right? And the duality quotient is just A1, so this is the map, right? So in many of these cases, you can describe, I think the Hamester and Morris, they have a complete description of this quotient, I think called the split case, and looks slightly like this, right? Which finite in many, I think the number of, if I'm not missing the number of sheets is at most 4 in this one.
If it's a simple.
Oh, it's simple, yes, simple, yes. At least 4 sheets at some point. In the case of multiplicative, there's even more sheet on the boundary of the monoid. You may have some strange numbers like 2 to some powers. I don't remember. It's something complicated numbers. It very much depend on the, if you want to extend the standard section to the boundaries, and there's a choice of the order of roots. And Alexis did it in his thesis, and actually every single choice give you one sheet on the boundaries and the structures. In this case, actually interesting. In this case, even in case of GLN, and just leave it to 2, and given to GLN. And in this case, the M mod G is actually the Châu scheme of A2, representing 0 cycle of length n into the A2, right? And you have this M rep, this regular quotient. Here you don't have to put any oscillator. And in this case, M mod regular quotient contain, and this is just regular, just mean that the commuting element or 2 commuting elements, so the centralizer is the right dimension, right? The way it contains one open orbit, which is the 6 cyclic. That means there's one that as moduli is replaced 1 element. And so for the regular, it contains M cyclic mod G, and this thing is the Higgs scheme of A2. The sub-scheme is the dimension of length n of A2, right? And so the map that we're studying, this map of M rep mod G, contain a piece of it is actually the residual singularity, the Higgs scheme equal to Châu scheme, right? And so this gives a very good perspective, and somehow you may be able to define what is the Higgs scheme for every group. You can just look at the M rep mod G and try to define a nice piece. One of the things is the main theorem in my drawing work with Morris say is that the map of M rep mod MG is not proper, right? In this case, not proper, but it contains something proper, and you can prove in general that this map satisfies the existence part of valuation criterion, not uniqueness, right? So there is very high chance that there is some kind of maybe some Mumford GIT condition, some kind of light bundles to specify some open part of it, which is have also the uniqueness. Then you'll be able to have a lot of residual singularities on this M mod G in very general setup. And one of the moduli space, so this is the at least in the case when the X is a curve, that implies the map is subjective. For every map into the, at least the zodiac regular semi-simple, into this M mod G can be lived into this. And over this, you have this now the map into the M rep mod G. again, it looked like a group, smooth group scheme and so on. And then, well, yeah, I think I'm running out of time. I don't want to say anymore, but there's, I think it looked kind of wide, but I think you can see there's been do it. But for moduli, you look kind of very much on from the invariant theoretic perspective, but there should be other problems, related to this kind of moduli space. Thank you.
Is there any question or comment? Very quiet this morning. Yes.
In this example, you mentioned the complement of this Hilbert scheme. Is that understood?
No. So actually, at least I have two open subsets. One is cyclic, the other is co-cyclic. It can be that on the dual space is cyclic, but without one being cyclic. It's likely that we die that's a union, but I'm not sure in the case. Even for this I actually don't know. I mean, maybe if you allow, I just want to say that I don't have time to talk about it, but it's a very fascinating question is this story of thermal covering, right? In this situation, we can actually study very refined detail about this group because it has it thermal covering. One single flat map, Galois map, that allow it to describe this regular centralizer in a very hand-on way. So we are trying to how in what extent we have this. You have this. You can define a flat covering of this regular quotient. And it turned out to be actually a hard question. So in all these cases, you do have it. I have no counterexamples. But even in this case of D equal to 2 and G equal to GLN, and this turned out to be extremely difficult theory of Hyman. So Hyman in these celebrated papers about the factorial conjecture or so on. The main ingredient is the existence of a projective bundle. And the projective bundle exactly cannot cover in this case. And as long as we do not have a kind of nice understanding of the Hyman proof, no way you can make any progress. But I really want to, if you somewhere have an idea that will be interested in understand in the counter examples or how you can construct, on the regular submersible locus, we have finite time covering, but why it extend to a flat covering and under what assumption? I really have no ideas.
Flat covering, you go what?
Of the regular quotient. Right? Regular quotient is the Hilbert scheme. It kind of you can think about regular is kind of very generalized Hilbert scheme.
So I have a question. You mentioned, the title of this conference, Hitchin system, Langlands duality, and mirror symmetry. So, do you expect any of this generalizations to? I mean, we know some play a role, but in general, to play a role in mirror symmetry?
Yeah, I'm no expert in mirror symmetries, but I really want to, one of the things I really want to understand this flat covering because I want to have J1 and J0 in general. Extend have J1, J0. This is kind of very, embryon of mirror symmetries in this invariant theoretic construction. That as long as I have this flat covering, then I can start asking these kind of questions.
All right. So I think we can ask questions of the coffee, but before we do that, let's thank Châu again. Thank you.